Okay, good.
Okay, now we're slightly switching gear now, because now we're going to put causality back in the arrows, which I'm very pleased to hear, and also responsibility. So we've got two topics close to my heart. So it's a great pleasure to introduce Hana Chockler from King's College, talk about causality and responsibility in formal verification and beyond.
Yes, thank you. Thank you to the organizers for inviting me. So the speaker before me was very cunning in not disclosing the title until the talk, so everybody was, on edge. I actually did something even more cunning. I'm not going to emphasize the things that are written in the abstract, but other things. So, it's even kind of higher degree of deceit. And the reason is that I initially planned to give a version of the talk that I gave already as invited speaker in another workshop that was mainly, exclusively actually attended by computer scientists. I'm a computer scientist. But being here yesterday and today, I realized that it's probably not a good idea. So I switched the emphasis in the talk. So it's causality and responsibility in formal verification and beyond. In fact, it's going to be a little bit of formal verification and a lot of beyond. But then, of course, I think it's actually only dawned on me today, I realized that my talk is different from others in a more fundamental way. And the way is this: there are no Bayesian networks in the talk. Right, so yeah, there are not a single Bayesian network. So sorry about that. My ambition now is to make at least the formal verification part accessible to everybody. So, tell me, scream or wave or ask questions if in the formal verification part you feel that I'm losing you. All right. So causality. When do we say that A is a cause of B? So of course there is this counterfactual approach, going back to Hume or even earlier, which is if A is a cause of B, if head of B, right? B. Where is B? I see B here, B is not there. A is a cause of B. If had A not happened, then B would not have happened. So it wasn't raining today. Yesterday, again, very typical weather. Usually it rains here in England, so usually this is a perfect example. Coming to a talk wet, of course, rain is a cause of the speaker being wet during the talk. Because hadn't it been raining, then the speaker would have remained dry. So it didn't rain today. Right. So in a slightly less hand-wavy way, only slightly, the counterfactual causality expresses the following perception of cause, which is, so we have a world in which A is true and B is true, and then if we were taking the same world exactly, but switching A to not A, then B would be false. Simple counterfactual approach. So it works well in practice in many cases. In others it doesn't. So let's look at the case where it does work. So here's an example. We have a forest fire that is caused by two campfires. This example is, by the way, taken from from Untitled Pearl and Halpern's paper on causality. So right. So in the first case, in the first example that we're going to look at, the two campfires started a forest fire, but they could only start a forest fire if both of them happened. So each campfire alone was not enough to start a forest fire. So there is an and, there is a conjunction between those two events that led to the forest fire in the forest. Now there's clear counterfactual dependency between these two events. It's hopefully easy for you to see. Each camper separately, each camper's carelessness separately is a cause, because if one of them would have changed their mind and not left a fire in the forest, then we wouldn't have had a forest fire. Now let's look at the modification of this example. So here is a modification. In this case, each camper alone started a big fire. So each fire alone would have been enough to cause a forest fire, but there were two of those campers. Now, a bit surprisingly, in this case, there is no direct counterfactual dependency, as you can see, because if that camper on your right, my left, would have changed their mind, then we would have still have had a forest fire, because this camper's fire was big enough to start a fire in the forest. So there is no counterfactual dependency, so applying this simple counterfactual reasoning, we get that neither one of them is a cause, which is a bit surprising. So when we come to fix the definition of causality, first of all, what we need to address is this redundancy, right? Intuitively, what we saw in the previous example is kind of redundancy. We had several causes, each one of them was enough, but there were several of them together. So we need to address redundancy. Several causes happened. We need to somehow incorporate this into our model of understanding of causality. Okay, another thing that we need to address is illustrated by the following example. So in this example also we have a disjunctive relationship. So each campfire alone would have sufficed to start a forest fire. But not only that, but also the first camper, that one, left the fire several hours before the second camper. So when the second camper came, apparently there was already forest fires, starting to spread from another part of the forest. So there was the notion that we are looking for, right, is preemption. So not only there is still no direct counterfactual dependency, but also there is a preemption. So the first camper needs to be a cause. It looks like it's reasonable to say that the second camper is actually not a cause, because there already has been a forest fire when they came to the forest. Now I'm thinking that maybe it's not really such a great example, because probably it's very unpleasant to go camping when there is a forest fire in the forest, but okay, let's ignore it. They were wearing astronaut suits and were oblivious to the environment. Okay, so two things that we need to address. One of them is redundancy. Several causes, each one of them alone would have sufficed for the outcome, but we have several. And second is preemption, so the order between the causes and the particular time when the outcome actually happened. So intuitively, the definition of structural causality by Halpern and Pearl introduces the extension. It extends the counterfactual causality to the situation where there exists some contingency in which B counterfactually depends on A. So has some kind of implicitly, this is actually a cloud. Yeah, I see what other people meant about the projector. There is a cloud here. Anyway, at least we can see what's written. So it's a progress. So implicitly here we assume that the person that is constructing the model actually understands the situation, understands what happened, has some knowledge about the dependencies and things that cause other things. So somehow implicitly and beyond the scenes, we have the observer who knows stuff, and this observer is able to construct a model which includes the variables and the dependencies between the variables, the functional structural equations which are expressed as the functions of the variables, and the context U, which says what actually really happened. So we'll have a variable for the campfire, and it will be assigned 1 because the camper actually lit a fire. So that's implicit. Let's assume that we're able to do that. So the contingency comes to address the redundancy of several causes. And the pictorial representation of this, we will see an example in a second so you'll understand better what I mean. So again, we have the original world in which A and C happened. Each one of those separately would have been enough to cause B, but there were two of them, right? Like those two campfires. So now we introduce a contingency. Same thing exactly, but let's remove the C. Let's remove the redundant cause. Okay, now we have A, C didn't happen, and we still have B. Okay? And now in this case, after the contingency, we have the counterfactual dependence, which means that now, if A doesn't happen, then B will not happen. Yes, the structural causality introduces an additional step, which is introducing a contingency, or considering contingencies into with the world. Note that contingency by itself does not falsify B. Yeah, contingency just brings us closer to falsification. It creates a counterfactual dependency. We still need to address preemption. Okay, so you'll see it in the next slide after some animation. So this is how a very simple causal model, or rather a network that represents a causal model looks like. So this we have two campers. Again, you are missing on all the fabulous clouds in the presentation because of the features of the projector. So we have first camper leads a fire and second camper leads a fire. So we have one CL and two CL. Those are two variables. They together cause the outcome, which is a forest fire. But the dependency here is OR. So each of the camper fires by itself is sufficient to cause a forest fire. No preemption, they came at the same time. Now, in order to capture preemption, we actually need to do some tricks. The trick is to introduce some additional auxiliary variables to capture the order between them. So now we say, okay, so let's introduce another variable that will say that actually the first camper started the fire before the second camper. Okay, so now we have, we don't have this direct dependency, but rather, so camper comes to the forest, then he starts a forest fire, and the second camper would have started the forest fire only if the first camper wouldn't have done it several hours before, several hours earlier. So the 2CF, the second camper, the variable that says the second camper started the first fire, is 2CL, meaning that actually he came and lit a fire. Otherwise, you know, the forest fire doesn't start by some applying magic powers. And the first camper didn't start the fire. Okay, so this is a dependency. So now that we've done that, we introduced auxiliary variables that express the order. So this is just comes to illustrate you that there is a way to introduce this preemption, to express this preemption feature in the model. In general, structural causality is, the concept of structural causality is very flexible, and in fact, everything you know you can drag into the model. Right? So the model becomes more and more complex, but it's possible. It allows you to do this. So the definition of cause, which is a very, very hand-wavy way to actually do the definition. If you look in the original paper, you'll see that it's much more complicated. But in a very informal and hand-wavy way. So a set of events X is a cause of the outcome, phi in the model M, that we know how to construct, and in the context U that represents the current state of events, if, one, there exists a contingency that creates a counterfactual dependency. So there creates a contingency and under which now if we change X, it will falsify the outcome. Two, the contingency alone does not falsify the outcome. So contingency brings us to the counterfactual dependency, but it alone doesn't go over the edge. And not only the contingency itself, but also any part of it. So this kind of, the definition is kind of like a living thing. It evolves. If you look at the first paper, it was one definition, it became more complicated, became even more complicated. And actually what I'm presenting here is not the last version, it's one before last version. So the next version, the last version for now, was presented by Joe Halpern in last year's paper. And the reason I'm not talking about that one is because all the applications I'm going to describe are actually refer to this one definition, not the last one. Okay, but that's just to tell you. So it's kind of, it's evolving, so we're constantly running after the definition. Right? So but of course, it's another reason to write more papers, because then you can update them for the new definition. But anyway, so the contingency or any part of it does not falsify the outcome. And in introducing the contingency, we're kind of trying to keep the causal reasoning the same. Okay, so the last part is mysterious, and actually I'm not going to focus on it too much, because it's not important for our applications, but it's done in order to ensure that the preemption feature still is maintained. And that's minimal. So minimal means that we cannot bring any relevant events into this set of causes. So the camper starting a fire and sneezing would not be a cause, because sneezing is irrelevant. Okay, so that's the one before last definition. This is what we're seeing now. I'll just tell you why we need to consider subsets of the contingency. And this is for the following reason. So the reason is illustrated by the following story. Note that I'm still not on formal verification. See, I promised that this part track did. I'm not there yet. So the model, what is the model? The prisoner dies if either A, load B's gun. So apparently B and C can shoot, but B doesn't know how to load the gun. But A knows how to load the gun, but not how to shoot. So if a prisoner dies if either A loads B's gun and B shoots, or if C loads and shoots his own gun. So both B and C can aim, but B doesn't know how to load the gun. So if the outcome is the prisoner's death, D, then D is expressed by the following Boolean expression, Boolean formula, which is A and B, right? Either A loaded B's gun and B shot, or C, where C loaded and shot his own gun. Let's group it in one event. So in the current context, what's really happened, the context describes what really happened in the world, in the past tense. So A loaded B's guns, but B didn't shoot. But C loaded his gun and shot. Okay, so A is 1, B is 0, and C is 1. Okay, so obviously the prisoner has died. The prisoner died, right, because C shot him. So clearly C equal to 1 is a cause of death. Now the question is whether A loading B's gun is also a cause of death. So this is a story that prompted the introduction in the part of the contingency because, so first of all, before I say because, I think we can all agree that A being 1 should not be a cause, right? Because the prisoner didn't die from the bullet. Yeah.
Can I just clarify, why didn't B shoot? Was it because he didn't want or because he was caught in the process, for example? And
this is not a clarification. You're bringing some other stuff into the model. The model doesn't care. This is what happened. B didn't shoot. Doesn't matter why. So first of all, A equals to 1 should not be a cause, right? Because D did not die from B's gun, not from that bullet that was loaded. So, but what happens if we take the contingency that includes B and C? So let's take the model, right? In the model, A is 1, B is 0, and C is 1. So let's take this contingency that includes B and C. Contingency means that we change some values. So let's change. So now I'm changing B to 1 and C to 0. Okay, what will happen? Now I kind of took the model, took the story, and I changed it to another story in which C didn't load the gun and shoot, but B shot, right? Now under this contingency, the prisoner's death would definitely counterfactually depend on A, right? Because B is unable to shoot an unloaded gun, correct? But this contingency is actually cheating. It's taking the story and replacing it with another story. It's saying, no, actually, let's now switch the causes onto the table. Let's consider the story in which D died not from C's shot, but from B's shot. So we're trying to prevent that. But note that if we're checking that any part of the contingency does not falsify the outcome, then we will see that taking this part, C, and changing it by itself will already falsify the outcome. So if, given that nothing else changed, but C now changes his mind, then the prisoner would have stayed alive, right? So this is why this introduction of parts of a contingency was brought into this definition, to prevent those cases, to keep the causes the same as it were before. And now I'm finally going to talk a little bit about verification. So formal verification, in general, the verification in computer science is trying to answer the question of how to verify computerized systems. So of course we want our systems to be verified as thoroughly as possible, because otherwise all kind of disastrous outcomes can result from using those systems, including loss of human lives, loss of lots of money, etc. Well, it should be obvious to all of us. And in general, when we're looking at this vast array of techniques to verify computerized systems, we can very roughly define them into two. One of them would be bug hunting, so we're looking for errors. And another one would be trying to ensure that the system is correct. So there is, of course, an order between them. So we're looking for errors, we're trying to fix them. At some point, we don't find any more errors. But the fact that we don't find any more errors, it's in itself is not really contributing a lot to our confidence if we don't know how thorough we are. We don't know lots of things about our techniques. So what we would like to have at this point is something that will be able to give us a sort of a certification of correctness, to tell us, yes, the system is correct. Okay, it's a kind of stamp. So the techniques that do bug hunting as opposed to certification of correctness are also mapped to types of algorithms. So in this corner, like boxing, in this corner we have the bug hunting methodologies. This we have for hardware, it's called simulation-based verification, when we try to run simulations on our chip and see whether it behaves strangely. Of course, in software we have testing, all kind of tests that we apply to our systems. And essentially they amount to checking the behavior of the system many times. And then they give us error traces. In formal verification, which is my area, we represent our system and the specification in some formal mathematical way. And we try to create an automatic proof. No, not us trying to see and prove it, but some automatic proof of correctness of the specification in the system. So we'll see this picture that describes this process in the next slide. But first of all, so when we have an error trace, right, this is not the end of verification. So we have an error trace here. This also doesn't mean that we're done. So now we take these error traces and then we go and try to fix the system with this error trace. Okay, so this is the process of formal verification. So we have some black box, intentionally black. It doesn't matter what happens inside. We feed it with some mathematical representation of the system, finite state machine, transition relation. It really doesn't matter. A formal specification in some formal language, temporal logic, other logic, finite automaton or whatnot. The black box does some processing, and then it outputs either yes, which means that it's correct, or no, and then it gives us a counterexample. So a counterexample is used to fix the system or the property and then to try to do it again. And eventually when the process is done, then we get the verification stamp. Right, so the problem here is actually a problem that sort of this process shares a little bit with testing. Although in testing the traces tend to be sometimes more understandable, but definitely in formal verification the counterexample that we are getting is not always helpful or self-explaining and useful in order to fix the system. Yeah, so we don't actually know how to fix the system when we look at counterexample. And some further guidance would be very helpful. So here's an example of how counterexample looks like for verification of hardware design. So this is part of a chip. And the counterexample will look like something much larger than this, with many signals and these wavy things. This is a timing diagram that says when the signal was up, when it was down. And we're supposed to deduce from this what went wrong. Why is it a counterexample? Where our specification failed. For software, the result of applying a model checker, which will look like this. This is a very condensed one, if you can see it. This is the state 227. This was a very short program, only 46 lines. So we'll have this huge kind of list of statements describing the values of variables in every state until you have the last one, the punchline, which is verification failed. Great. Not really helpful. So we don't really understand the counterexample without further guidance, which is sorely needed because we need to fix the system. So how do we explain counterexamples and verification? And how do we show the user what went wrong? So, so this, I think the previous one also had these dots. These mysterious red dots are actually explanations. So this is one of the real quite simple specifications. It's actually, it says it's not very complicated when you try to break it down. It says that new transaction shouldn't begin until the status valid from the previous transaction arrived. But it's expressed in this temporal logic, which makes it a bit user unfriendly. And then we have lots of signals, but then when we go and we point the causes, now the causes, this means that this diagram, this counterexample is represented as a causal model with respect to the outcome, which is the falsification of the specification. And we have the values that correspond to the values on the actual counterexample. And then we apply the definition of causality in order to compute the set of causes for the failure of the specification on the trace. And then those causes will be the values of variables in certain cycles. So in this particular case, the specification failed because the what happened, the other transaction began before the status valid arrived from the previous transaction arrived. If you look at the diagram, we can see that there is start of the transaction in cycle 9, where status valid hadn't arrived yet from the previous transaction. Okay, so this was implemented, and now instead of thousands of cycles and tens of variables, the user only has to look at several causes, so several red dots. So which was, of course, very helpful. And this was implemented when I worked at IBM Research. So it's actually part of the verification platform. The users absolutely love it because it makes their life easier by several orders of magnitude. When it was taken out for maintenance, they actually phoned and complained where this is. There is actually quite a lot of work in explanation of counterexamples in software engineering in general, and verification and in testing. There was a tool that's even called Explain from several years ago that didn't work on causality. It worked on concepts of trying to find the closest good trace in the program by Alex Gross. And then there is a whole area of statistical analysis for fault localization, which is a very active research area, essentially applying all kinds of statistical measures to the list of results from executing many tests. So it looks for correlations between statements and values of variables and the faulty outcome. Of course, the problem is when we look for correlations, we can find all kinds of interesting correlations. You can see on this website there are many other interesting correlations. So this one, for example, is a correlation between number of people who drowned by falling into a pool and films in which Nicolas Cage appeared. There is another one, I think, there are plenty, basically. I think there is a correlation between number of suicides and, I don't remember. And what? And country and Western music, yeah. Actually, I can see, never mind. But yeah, so if you look at this website, you can see that correlation doesn't mean causation at all. But maybe in software, when looking at the same program, maybe the claim is a bit more justified. Okay. So, responsibility. So why on earth do we want to extend causality? It's a great concept. We use causes, we apply them to this counterexamples. It was very useful. We got lots of good explanations. So why do we want to extend it? So the thing with causality is that it's kind of it's a 0-1 concept. So either something is a cause of the outcome or it's not. Well, something might be a cause, but its influence might be very tiny, or this can be a massive cause. So we would like to distinguish between them. So essentially, the concept of responsibility introduces a quantitative measure of causality. It says, let's judge the influence of a cause by measuring the size of the contingency needed to create counterfactual dependence. So this is essentially 1 divided by k plus 1, where k is the size of the contingency, and it's honestly it's quite intuitive. So you'll see why. So here, for example, we have a voting system. We have elections. Incidentally, I think this is yeah, those are Lincoln and McClellan, 1864. So in the first case, we have Lincoln getting 51, McClellan getting 49. Let's assume that 50-50 is not winning. 50-50 will mean that the election will have to be held again, something like this. And then in the bottom case, we look at another situation in which we have 90-10 for Lincoln. So I think it should be fairly obvious in this by now, by this slide number 21, that in both cases each of the blue voters is a cause of Lincoln winning, right? Because there is a contingency that creates a counterfactual dependency. Now, what is the contingency in the top case? In the one on top? So actually, sorry?
A subset of two voters voting wrong.
Yeah, so in the top, on the top figure, actually, there's no contingency. Each blue voter is by itself a counterfactual cause, yes, sufficient to change the outcome, right? The top part, one blue voter changes their mind, Lincoln doesn't win, correct?
Assuming they only have one alternative option, they could
Yes.
just abstain.
No, assuming that they have only one option and assuming that 50-50 is not a win. Yes, two assumptions. Okay, in the bottom one, what is the size of the contingency?
Sorry, but I want to follow up. I mean,
Yeah, sure.
So if he hadn't voted for Lincoln, it's not the same as if he'd voted for McClellan.
Yeah, so this is our model. That's what I said. In our model, they can either be blue or brown. They can either vote for Lincoln or McClellan. They cannot not vote. But of course, it depends on the model. So if the model would have been richer, if the reality would have been richer, I don't know what reality was. It's not important for now. Then we would have introduced, of course, other values into the model. But let's assume that this is our model now.
Secret vote, right? They cannot change their vote based on how they see other people vote.
No, everybody votes at the same time. Doesn't matter secret or not. Yeah. So what's the contingency in the bottom one? Right. So you agree that there is no counterfactual dependency, right? So one of them changes their mind, becomes brown, then still Lincoln wins. So what is the size of the contingency?
40 at least.
Right. So the size of the contingency is 39. So, right, once you change the minds of 39 people, then it will be again 51-49, and we will be in this situation as well. Correct? So each voter now, each blue voter now is 1/40 responsible. So 1/39 plus 1. 1/40 responsible for the winning of Lincoln. So this illustrates, this explains why the concept of responsibility is as it is, and of course it sort of conforms to our intuition. So in the one responsible means critical, and the lower the responsibility gets, the less the influences of this cause on the outcome. And surprisingly enough, it was again very useful for formal verification. This is a drawing of something that's implemented in Intel. I didn't work in Intel, I worked at IBM. This was a student who worked in Intel. When essentially, in order to figure out the value of the circuit at the end, they take the circuit and they unroll it many, many times. So they get this long graph, a cyclic graph, and then they try to figure out the minimum number of variables, so the most influential variables that they have to assign in order to figure out the outcome. They don't want to assign all of them. And what works well is apparently assigning the most influential causes, the ones with highest responsibility. So compute all the causes, order them by their responsibility, and then started assigning from the highest one. And this showed the best results compared with engineers assigning based on their knowledge, intuition, or heuristics, or whatever was. Like the doctor was heuristics, so the engineers with heuristics worked worse than this technique. Okay, so let's go a bit further. Let's now discuss the degree of blame. So what is blame? No correlation, no moral associations with blame or responsibility. Just we needed another name. So what is blame? So now, not always we know everything, or not always every agent knows everything. So they assume something about the world, and they attribute some probabilities based on their knowledge or confidence to what actually happened in the world. So the blame, as we defined it, is the expected degree of responsibility over all possible worlds according to the knowledge or belief of an agent. And it's better, it's easiest to understand it if we look at the example of a marksman, of 10 marksmen. Not the style of examples in this presentation, right? People shooting other people, marksmen. I think it's going to continue in this style until the end. So we have 10 marksmen who are going to execute a prisoner. Apparently, so it turns out that only one of those marksmen has a live bullet. Others have blanks, but they don't know which one has a live bullet. Okay, so they all shoot. So if we know everything about the world, including who has a live bullet, then of course the responsibility of the marksman with a live bullet is 1, right? There's counterfactual dependency. Nobody else had any live bullets, so it's only this marksman. And the responsibility of others is 0, because you cannot kill a person with a blank. Now each marksman has no idea who has a live bullet. So from the marksman's point of view, each one of the 10 possible worlds is equally plausible, correct? So each one of the 10 possible worlds has a probability of 1/10, 0.1. Now in the world in which they have the live bullet, they have responsibility 1. In all others, they have responsibility 0. So the expected average, the expectation of the responsibility, which is blame, is 1/10 for 1/10 for each marksman, right? Okay, so this is the main difference. So they kind of share the blame, and the blame becomes lower. But of course, had we known everything in advance, then one of them would have had the sole responsibility for the death of the prisoner. Okay, and finally, let's talk about a case in which we applied all the structural causality. This is the beyond part. So the goal here is to aid in legal inquest and inquiry. This was a paper with Norman and Dave and Jeroen Keppens, who was supposed to be here but cancelled at the last minute. So there was a case that was kind of made the headlines in all the papers. Of course, not only in Sun, but in other more respectable papers as well. We call it the case of Baby P from 2007. So the story is following. So this is a child, baby Peter, his name was Peter, was born in March 2006. And then he died from abuse when he was 17 months old on 3rd of August 2007, when he was found dead in his cot, and post-mortem examination actually revealed lots of injuries, including a broken back, broken ribs, and all other injuries that he suffered through an extended, long period of time. So when we look at the timeline, we see that many things happened that perhaps should have triggered some intervention of the authorities earlier, and they didn't. So there was a story. He lived with his mother, with Tracy Connolly. Then she got a new boyfriend who was potentially abusive. The new boyfriend, Stephen Barker, moved in, and then there was the first time that the GP, the doctor, saw bruises on the baby's face. And then the mother was arrested. Then she was released. Then there was a social worker who said actually something might be wrong. She sent letters to the authorities, a whistleblower. Then he was admitted to hospital again with bruises. Then he was again admitted to hospital. So the mother was again arrested. Then she was again released. Then in June 2007, the brother of this abusive boyfriend, potentially abusive, Jason Owen moved to live with them, with his 15-year-old girlfriend. And then the family had several visits from social workers after that, and then the injuries that were assumed later to be present already were missed by the social worker during the visit, because the boy's face was smeared with chocolate to cover them. And then on August 1st, 2007, the boy was examined at actually the child development clinic, and nothing wrong was found with the boy. And then 2 days later, he was found dead with injuries that probably were present already during this examination. So as a
chocolate factory was accused.
Of course, actually everybody but maybe it's a good idea now to bring this into the explanation as well. Right, so what happened then? So there was a prolonged process of legal inquiry following this, BBP's death, in which, so they were found, the boyfriend and boyfriend's brother were found guilty, and the mother pled guilty. Actually, the mother is released apparently a couple of years ago. But more than that, there was an inquiry into the GP practices, into the child development, into the children's services, the local authority, the hospital, the social workers. Everybody was kind of brought in, the judges who arrested the mother and then released her again, the NHS, so the GP who saw the baby P on 14 times and didn't escalate the case. The doctor this is the doctor who saw him 2 days before death and missed the broken back. So she was just recently found guilty of professional misconduct because she was out of the country. But it's a very, very long process in which some of the things were decided and then reversed. So the local authority director of children's services was sacked, but then later reinstated. Then she sued for damages. Still kind of not clear. There were many people and many authorities involved in the in this story, and it's not clear what was the influence, what was the responsibility of which one of them in this outcome. So what we did in the paper was that we constructed a causal model. So in fact, we constructed a causal model in iteration by constructing a crude model and then refining it, adding more and more information. So we started with a very straightforward assumptions, and one of those people, grown adults in the house, must have caused the major injuries that led to baby P's death, and others must have allowed these injuries to happen by not reporting and not preventing them. Then we extended it to include other factors such as the pediatrician, the GP, the hospital, the child development clinic. This is only one branch. We had many branches. So this one is related to the examination that happened on the 1st of August. So obviously the final model was quite complicated. But so about the case. So the case was complex, right? So the model was complicated. So it's not a surprise. Many factors, many players. As a result of this case being complex, some decisions were made and then later overturned, like the case with the children's services, who was later reinstated. Then the process of constructing a causal model is actually helpful in guiding the inquest. So we started constructing a causal model, then we saw missing pieces, and we went to look for the missing pieces and to fish them out of the existing documents. The causal model allowed us to input what happened, what we know as a fact, and also our beliefs about what happened, so what is likely based on the history of these particular people or how the bureaucracy works. It also allows us to input our beliefs about how the world works in general. Right? So for example, one of the things we decided is that it is more likely if there is a mother and an abusive boyfriend, it's more likely that an abusive boyfriend causes injuries than the mother, in general. In general. Again, you might decide something else because you might have other beliefs. So as we said, as a result, so the model was complex, but what we saw is the model was actually modular. So this is a good news. The model was modular, so we could refine it in stages. So we could focus on one branch and another branch, refine this, refine that. and compute the responsibilities and the blame of involved parties in stages per each part of the model. So every part can be analyzed separately. Diagrams were more helpful than piles of documents. And this looks promising as a tool to aid in the process of inquest and inquiry, not to be brought in front of the judge, but maybe to guide us or to support our beliefs, or to actually give some quantitative, give some numbers to what we think about the guilt of the involved parties. Right. So that's all. So if we have time for questions, great. And then after that, I think we have time.
Time for some questions.
Thank you very much. One thing as a statistician that troubles me about the applicability of these methods in my domain is that they seem to leave any room for stochastic uncertainty. So if I light a campfire, maybe a spark will fly and catch a dry leaf, and maybe a forest fire will start, and maybe it won't. And I might have some probabilistic understanding of that process, but I don't think there's a logical relationship between the outcome and the various possible inputs. So is there any way in which your models could be expanded to take that kind of uncertainty into account?
So the concept of actual causality, which was based on the structure equation, deals with what happened. So it happened already, right? There might be some, of course, you might not have known how large should the fire, your campfire should be to start a fire, depending on the wind and all kind of stochastical interference. But once it happened, it happened.
Yeah, but the counterfactual isn't clear. What would have happened if this hadn't happened could also be stochastic.
Right. So the way to bring this into the equation is to use, I guess, blame instead of causality by introducing many possible worlds in which in some of them the fire would cause the forest fire, in some of them it won't, with probability distributed accordingly. This is what the model allows. This is the way that I can see it. Yeah.
No, but as I understand Pearl's model, the causal models, the relationship in the model are always deterministic. The only way by which you can introduce uncertainty in Pearl's causal model is by introducing endogenous variables which are uncertain. For example, can you go back to your model for baby Peter?
Yes.
You mean exogenous noise?
Which endogenous are the ones that are influenced by others? Which one did you mean?
I mean exogenous.
Exogenous, sorry,
Let me
exogenous.
see.
Exogenous, yes.
Yes.
Yes, here you have the arrows pointing from TASA to P to PD
Yes.
are deterministic. And the only uncertainty is in the variables if Dr. Al-Zayat is sufficient.
So you're talking about the actual,
and so on.
you're talking about structural equations,
Here
right?
You suppose from a legal point of view, here you take for granted that they are the cause of the death.
I thought we put probabilities there.
No. So what happens is, yes, there are probabilities to the values. The model reflects our understanding of what works. So actually, the arrows don't mean that this immediately causes death. It merely means that the PD, or death of baby P, is influenced by those variables. Right? The arrow doesn't mean if this then immediately death. No, so this is
Probabilistic way.
this is
Probabilistic, the model doesn't work.
So this is the equation that expresses the dependency. So it means that in order for him to die, we, according to our understanding, so none of the adults would have saved him, right? Because if he was saved, then he wouldn't have died. And one of them would have caused him injuries, at least one of them would have caused him injuries that caused his death. Which of them actually did this? Now we don't know.
Caused with probability 1.
No. Which is, wait, which is,
That's logically certain.
this is,
It's a logical relationship which
Yes.
doesn't allow for uncertainty. That maybe he wouldn't have died even if that situation had arisen.
so if at least one of them caused him injuries that caused his death and none of them prevented him, then he died. If you say that actually he wouldn't have died nevertheless, then there were other factors.
You're getting circular. If one of them
Yes.
caused injuries, caused his death, I mean, you're defining cause in terms of cause.
If one of them inflicted on him injuries,
then he might not have died. It might not
inflicted
have
on
been
him
more fatal.
inflicted him fatal injuries, at least one of them inflicted him fatal injuries, this is how it's defined, and none of them prevented those injuries, then he would have died.
Okay.
Right?
But to
So
say
this
it was
is
fatal is to use a causal term, I'm afraid.
fatal.
That it did cause death.
Yeah, so in fact, all this is analysis after the fact, which actually maybe plays into our advantage somewhat, because the injuries were deemed to be fatal in the post-mortem examination. Into pre-mortem, of course, it would have been very hard and would have, been gone. We wouldn't be able to construct such a model to predict something. But we didn't predict. He died. The baby died, and he was found to have injuries, fatal injuries. So somebody must have caused.
I'm sorry, but the model is not just a model for what happened, it's a model for what could have happened. And in alternative scenarios where you negate some of these things, that formula just might not be appropriate. In the counterfactual world, it might not be the right formula.
I think we partially disagree here. So the main thing that I disagree on is that it's not about what have happened. What happened is the outcome. The outcome happened. The kid died. Right? This we don't disagree upon. The kid died. Now he died from something. He didn't die from natural causes, as was concluded in the post-mortem. So it's not a medical examination. This model does not reflect the medical examination. It reflects this kind of guilt of involved parties. So he died, and he died from injuries from fatal injuries. Now, I agree with you about that. We don't actually know what happened, what led to those injuries, and who inflicted those injuries upon the kid. And this is why, of course, we attributed, as Dave said, we attributed probabilities to each of those variables that we introduced into the model. And our knowledge of what actually happened to what variables were included in the model is taken from the existing documents that describe the case. That's the only thing that was available to us. The probabilities that were attributed, again, are based on knowledge or belief or understanding that was the result of this legal inquiry. That's what we had. We took it and we expressed it into this in the structural model.
So can I ask you a question? Just if it was more like a kind of causal Bayesian network, that wouldn't help you, would it? Because you think that they.
Well, there are two kinds of causal Bayesian.
Yeah.
One which is looking forwards, and one which is looking back. Okay. If you're just predicting things, what would happen if I intervene here? That's fine. If you're asking what would have happened in other circumstances, looking backwards, then there are all sorts of criticisms you can make about the way that is modelled.
So is there an alternative that you would subscribe to?
Well, I think a lot of the questions are ill-formed, personally.
But in this case, we might really want to know the answer.
Yeah.
And what system would be best to try and explore it.
Sorry, just a finger on it. There are quite a number of causal power measures in the literature for stochastic causation. And so this is a subject of some debate as to what the best measure is, or in fact I think for different purposes different measures are good. By stochastic causation we're talking about, I think, the sort of thing that you're worried about, such as there was smoking which may have caused the death or may not, we're not sure. So the inquest doesn't conclude that.
He wants to go backwards. I mean, those power goes forwards, but you want something that goes back. Power just tells you the power of the causes to produce the effects, but we want to know.
Yes, but you can also infer, so you can use it to sort of attribute probable blame to a particular cause because it was the most likely thing to have caused the effect. So you can run it both ways.
Another question?
I mean, your goal using this model is to apportionate the responsibility of the social workers.
No.
Why
No.
not?
Why?
Then you take
no,
for granted
sorry.
the responsibility
No,
of
no,
these
no.
people in causing the death.
No, it was one of the first steps. It just one part of the model. Then we expanded it. Then there were other things. No, sorry, this is misleading. This is only a part of it. This is what I said. Is the model could be constructed by adding it. It's modular. So this is a part of people who lived in the house at that time. Then we expanded it. You see another arrow coming in. So of course the formula became more complicated. So this is a branch that is concerned with the examination of the child development clinic on the 1st of August. Then there was another branch, which I'm not showing because the slide is not big enough, of the social workers. Yet another branch of the children's services. I'm not focusing the blame on the people living in the house. No, we're able to compute responsibility and blame of all the parties involved by applying the model. That's what I was trying to say.
Oh, okay, sorry.
No, it's the time.
Sorry, okay. Thank you very much, Hannah.
Okay.